Welcome to this week's lesson of Senior Computer Science Club. Today we're going to be going over a graph theory technique which some of you may know, some of you may not, and it's going to be a little bit more advanced. It's going to require some more intuition, but the truth is this graph theory technique isn't as common. It's actually kind of rare because the implementation is kind of straightforward. So if it's going to appear in a problem, it's going to have something with it, because otherwise this kind of problem would be too easy. And yeah, it's just not as common, so I didn't feel like it was necessary to teach prior to the CCC because there was a very, very low chance of it coming up. But as you might be able to see by the file name, the algorithm is called Floyd-Warshall. So let's just have our template code in here, and then we'll go over what Floyd-Warshall is. Okay. So, what is Floyd-Warshall? Or what is the Floyd-Warshall algorithm? It's pretty simple. It's a shortest path algorithm that isn't as common as Dijkstra. However, it has its use cases. So yeah, the shortest path algorithm, automatically people are going to think of Dijkstra because it's intuitive. It's just having some queue with the minimum distance and then putting it in and then always trying to optimize, trying to go further. And yes, that would work for just shortest path between two nodes. But what this algorithm solves is the problem of finding the shortest path between all pairs of nodes. So a regular Dijkstra's will run at a time complexity of O of E log V. Big O of E log V. And so if you did it for all pairs of vertices and the and since there's n choose 2, which is about n squared, it's actually n squared minus n all over 2, but the complexity of that is n squared. If n was the number of vertices, so in this case it'd be v squared, number of vertices, then that means our final complexity would be big O of v squared e log v. And also, so that looks really, really big. It's got a lot of, it's got a v, and then an e, and then a log v. And then the memory is also really bad because you have to store all the, not only do you have to use the graph and store all the nodes and the connections and the weights of the edges, but you also have to store the priority queue each time. So the amount of memory that gets used up and then cleared and used up and cleared, it just gets really big. So it's best to not use Dijkstra's when you're asking for the to find all pairs, the shortest path between all pairs of nodes. And so what are the use cases? Well, it's simple. Floyd-Warshall has a better time complexity of big O of V cubed. And the space complexity is big O of V squared. So it uses V squared amount of memory with these number of vertices or nodes, and then the time complexity is O of V cubed. And the reason, the case in which we use this is if there are less than or equal to about 500 vertices, but there are a lot of queries. Because what Floyd-Warshall wants to do is once you find the distance between all pairs, then you can just say, when you ask, hey, what's the distance between this and this? And then you already have all the answer because you're storing all the answer to all pairs. So that's it's a trivial question. You're just getting it out from your array of shortest paths or shortest distances between those two nodes. So that's the idea of when to use Floyd-Warshall. Now, how does it work? Well, if dist at if this and the size would be v and v was the size of was the array holding the shortest path. Floyd-Warshaw's algorithm uses a simple principle. That dist at I, from the distance between the vertex I and the vertex j is equal to the minimum of just the distance in between them from the just from your adjacency matrix. If I and j were connected, that would be the distance, or otherwise it would be dist at I comma k, or I to k, plus dist at k to j. For all k, that's a valid vertex. And the reason is because you're saying, okay, I want to go from I to j, but then instead it may not be as efficient to go directly from I to j, and you have some intermediate step in between, so you distance from I to k plus the distance from k to j. It's kind of like chaining them together, so you get I to k to j. And so you start at I and you still will end at j. So that's why, so that's the idea of it working. But if you test all possible k values, you'll always get a, you always end up with the best distance from I to j. And because if you pick any two pairs I to j, that means you're going to have to run it of big O v squared times. And then for each v, you have to, for each k value, which is another factor of v, you have to check this condition to minimize the distance between I and j. And so that's another factor of v. So then your total time complexity would be OV squared times OV v, which is big O v cubed. And so that's where the big O v cubed comes in. Now, let's go ahead and see the implementation. All right, so let's go ahead and start that. All right, so let's say we were given let's actually put a new comment. We are given an adjacency matrix. Whoops, an adjacency matrix called adjacent, and the size is v by v, and the vertices are labeled from 0 to v minus 1. So first, we're obviously given v. Given v, the number of vertices. And then you're given the adjacency matrix, so the list of all pairs of distances between the two nodes, and then we'll go from there. And so we'll say that if the adjacency at -1, if the adjacency at ij is -1 for any values ij, then there is no immediate connection between the two vertices I and j. Otherwise, there is. And you can see that even if you weren't given it like this, you can always convert to something like this. So it really doesn't matter. Okay, so now let's go ahead and see. And then after we'll say, then answer some queries of given a start and end value, calculate the distance. So that's what the generic Floyd-Warshau problem would look like. Now let's see how that's going to be implemented. So first we're going to take in v, our number of edges. Actually, I should probably make some variables. So int v, and then int adjacent. The adjacency matrix is, let's say we have we restrict v to be less than or equal to 500. So let's just have the adjacency matrix as 505 by 505. And better yet, because we want to promote good coding, let's define a max size equal to max v. So you don't use magic numbers. And if you don't know, magic numbers are numbers that you can't immediately tell what's the significance of it. And so you're going to have int adjacent of max v, and then now we just need int dist max v and then max v. So this is the resulting 2D array holding all shortest paths, and then this is the adjacency matrix. Alright, so let's get started. So we're given v, and then now we're gonna get our vertices. But a key principle here is that the distance between a node I and node I is equal to 0. And yes, I said intentionally node I, because you don't have to do anything to go from one vertex to the same vertex. You don't have to travel any distance. So right away, we can assume that all the distances that are going to be given are going to make sure that adjacency at I and I is 0. So that's what we're going to make sure we do in our sample input, because that's just how distances work. All right, but it's not really a key principle. Just note that the distance between a node I and a node I is 0. Okay, so now for int I equals 0, I is less than v, I plus plus. For int j equals 0, j is less than v, j plus plus. See in the adjacency matrix at I and j. So that's me the length between I and j, and then after you're gonna have your distance array being set to something. But at first, what we should do is set distances to an arbitrarily high value, just so that we don't have to deal with any issues. And so we can just do that inside the for loop as well, because we're only working between 0 and v in both dimensions. So dist at I, j equals, and we'll make it really big, so we're just going to assume that's just not going to, we're going to use that, that's not going to hit this really huge distance. And we'll just go, not quite int max, we'll go 10 to the 9. 1, 2, 3, 4, 5, 6, 7, 8, and then one more. And then, so if the adjacency, the adjacent value between I and j is equal to -1, or is not equal to -1, then we can modify the current minimum distance between I and j to be the adjacent distance between I and j, just by traveling along that edge. And I do not equal to -1 because if it is -1, then there is no distance. And so at the start, we're going to take the distance to be 10 to the power of 9, or 1 billion, I believe. Okay, so now that we have that down, let's get our Floyd-Warshau algorithm going. Floyd-Warshau algorithm. And it's pretty straightforward. Remember, you're just going to consistently use this condition. Test all I, j, and k values between 0 and v, and then modify the distance between vertex I and a vertex j, and that's going to be equal to the minimum of just that, or the using an intermediate vertex in between, and that intermediate vertex in this case is k. So it's pretty straightforward what we have to do. So for int I equals 0, I is less than v, I plus plus. For int j equals 0, j is less than v, j plus plus. For int k equals 0, k is less than v, k plus plus. And then simple as saying dist at I at j equals min of dist of I at j, comma, dist of I of k, plus dist of k of and j. And that's literally it. Now we can go ahead and test it. and we'll do some inputs. Like we'll go for 5 inputs. For int I equals 0, I is less than 5, I plus plus. And then we'll take two numbers, a and b, cin a and b, and then we'll do a condition here. If dist at a to b is equal to this arbitrarily high value, then we can conclude that these vertices are not connected, and then we can end there. And then otherwise, we just say cout the minimum distance between those two vertices is, and then we just push out the answer, or see out the answer, dist at a b, and then just end it off with that line. Maybe put a period there too, just to see why not. Okay, so we'll do that, and then after we'll even test out the entire thing. So let's put a random, let's make a sample data right now. So we'll go 5, and so that means we're gonna need 25 values. We'll have 0. We'll just have I'll just fill this in with zeros and then after change it, because I don't. I just want to make sure it's pretty clear what I'm writing. All right, so I'm going to assign random values, and I'm going to make sure that everything along this diagonal, which is dist of I at I, is 0. So I'm just going to put random values in. So 0, 4, 6, 11, 17, 5, 8, 16, 7, more numbers, 4. Actually, now that I think about this, we can't just have randomly assigned vertices, because the distance between one vertex and the other, so the dist at I and j has to be equal to dist at j and I. So there's got to be some symmetry here, so I can't just assign random values right off the bat. But actually, let's just go back to what we had before and just modify it. Okay, so this would be a 4, this would be a 6, this would be an 11, this would be a 17. And then let's put another space here. Let's put multiple spaces just so it's easier to read because of just the alignment. If you don't understand what I'm doing with spacing, don't worry about it. It's not really relevant, but yeah. Okay. So we have that. Okay. So now we need symmetry along our in our thing. So we're gonna have a 16 here, and then this has got to be an 8. This has got to be a 5. Okay. Now we need random values right here. So let's go 9, 2, and 1. And so we're gonna have 1, 2, and 9. Okay. So it's good that we made the sample data, because otherwise the program probably would have messed up completely. Yeah. So as you can see, if you took a line here and you put it across this diagonal, you see that there'd be symmetrical, because the distance between vertex v1 and vertex v2 has to be the same as the distance between vertex v2 and vertex v1. So yeah, that produces this symmetrical thing. But yeah, okay. So we are good to go and test this out. So let's see. Let's make sure that, hopefully that this works. If not, that'd be not very good. Oh, okay. Yeah, I pasted the input twice. Sorry about that. Let's try again. Okay, let's just close these so we can see the terminal better. Okay, so now we have our data processed, and let's see the distance between node 1 and node 4. The minimum distance between those two vertices is 5. Now, how do we get that? So node 1 is node 4 is 4. Wait, did I mess up something here? Okay, let's think about how our input was processed. So with all the data here, this would be node 0 and this would be node 1. Oh yeah, node 1 and node 4 is just simply 5. Yeah, okay. Yeah, that would just be it. Okay, so that was an example of a vertex that it was just best optimized by just going through that spot itself. Now let's try doing something else and seeing if we can find a location where it's not necessarily best. Okay, 2 and 8. All right, so let's actually change this because it's gonna be tedious to find the best distances. So instead of just having this input, let's just print out the distance between I and j. And who knows, our sample data might have been really bad, and it turns out that the adjacency matrix is the minimum distance. I really hope that's not the case, but can't do, right? All right, so dist at I and j, and then we'll put a space here. And then after we'll go in end line here, and we'll see how it works. So that means that we don't have to pass in any inputs after, just get in this data. Okay, so we had 0, 4, 6, 6, 9, 4 through 4, 0, 3, 2, 5. So, okay, so as you can see, some of the data did change. Sorry about that. Some of the data did change, like for example, this 9 is no longer 9. It was a 17 before in the adjacency matrix, but it's now a 9. So, yeah. And that was actually found by going from 1 to 2, and then from 2 to 5. And so that's 4 plus 5 is 9. So that's the idea of floating washout. And yeah, it's pretty straightforward when you think about it, really. And it just uses the idea that the minimum distance is just using, it's either at the minimum distance at every step, or it can use the intermediate vertex. And it'll make sure to always get it, because even if it's not optimized necessarily, when it loops back around and all the you go back to j and I and j are swapped, then that means you're going to go through and do all this again. So it'll be guaranteed to be optimized. And yeah, that's the idea of floating washout. Let me know if you have any questions. I'll be sure to post questions on this. There aren't many, but and they aren't necessarily straightforward either. But I'll be posting them once I get them ready, and that'll be probably Friday evening, Friday afternoon, somewhere around there. And yeah, hopefully you guys learned something about floating washout, and let me know if you have any questions. And yeah, I'll see you guys next week. Bye.